Okay, it is my pleasure to introduce Victor Yodaiken again. He hasn't changed since he was here this morning. Victor?
Okay, great.
You got your mic?
I got the mic on supposedly. I'm not going to be pretending to be Mark Weiss, so I'm just going to do this talk for myself. So what I want to talk about is MiFID II implementation issues and lessons learned with attention on one particular lesson. And it's really sort of on the practical aspects of what happened over the last year. And so I have this sort of sad story. Many people suffered over the last year trying to implement MiFID II, although there were great successes. So the first thing is, it was a long year. Last year was a very long year for our business and for many of our customers because everybody was rushing to reach the standard. And the amount of labor invested in reaching the standard is pretty high. Many firms started off way out of compliance, and they needed an enormous amount of work, not just in terms of technology, but in terms of their own internal organization of trying to do this. We worked with a number of very large banks and financial institutions, but also a lot of small ones. And in toto, there was a huge amount of engineering labor. And what we found, of course, is for some firms, it was really not a big deal. And for some firms, it was an enormous effort because they were so far out when they started. So in this talk, what I want to do is I'm going to do two parts. The first is I'm going to give some sort of very high-level generic lessons. And then I have saved one for the end. And then I'm going to go and talk about sort of the subject of that panel that we had earlier, which is maintaining compliance and proving it, which is sort of at the heart of the work that people did. So the first thing is, this is not easy, and as Chris Lord pointed out, a lot of the difficulty comes from the fact that the networks that are operated by financial trading firms are extremely complicated often and very large in many cases. And so there's a lot of complexity in trying to get time delivered over those networks reliably, and it involves knowing a lot about how the network works. There's an enormous amount of complexity, a large variety of devices. There are a large number of servers that have different capabilities in them, and it requires people to have a great deal of knowledge going from, how do you configure the networking on your application servers to, what goes on in your Aristas or Ciscos and down the line of all the way to your antennas. So the first thing is it isn't easy, but on the other hand, it's just engineering, it's not magic. And this goes back to what I was saying earlier about some of the comments we saw at the SEC site when they were talking about regulations. Some of the firms that commented were essentially saying, they were talking about it as if this was some sort of magical process that you needed special information for. And really, it's just like anything else in the networks. But my first point was these networks are not trivial networks. It's easy to overestimate it. So the next thing is, this is a general lesson of modernizing the plant. I mean, a lot of the difficulties that people had that we saw were just, they had old equipment and it wasn't really up to the job. So my example is, if you have a GPS clock that's 8 years old that barely functions sitting in London and you want to connect across some shared cable to Chicago, you're not going to be able to get good quality clock sync on it. And we saw a lot of people essentially attempting to force that. And it never worked out very well. So that's one issue. Another issue, a related one, is to not underpower critical plant. And the example I have for this is we had some customers who were running our compliance server. And so compliance is archiving all this, bringing in all this data and archiving it and building a database. And we've had customers go, it's been running for 3 days and it doesn't have any result. And eventually we dig down and what is this thing you're running it on? It's a virtual machine with one virtual CPU that's running at 1 gigahertz with not enough storage that gets swapped out every 10 seconds, for a couple of seconds. And you just can't get that thing. It won't do the operation. And I think that many people had difficulties understanding that clock sync and record keeping for clock sync is a computational activity and a networking activity that requires good equipment, and you need to upgrade for that. On the other hand, the networks in finance are so far ahead of the networks in general enterprise computing. People are used to 10 gig networks or 20 gig networks, and or 40 gig networks, and they have high quality switches with low latency. So many of the problems that we've seen in some other industries don't occur that much in finance. The problem in finance really, in many cases, comes down to companies with, especially older companies with older equipment. We found one company, one bank, that was running critical services on Windows ME on some PCs that they had somewhere, and they didn't know anymore how to move it. And that was an issue for them. So now I want to go to something more concrete, which is maintaining compliance, improving it, which was the thing where we talked about before. And here, I think this was a conceptual difficulty for a lot of people. They would not really know how to go from having some sort of standard that they wanted to go to and sort of knowing how to measure it, knowing how to validate it. So you have something that's telling you how close it is to the time, and then you have to ask the questions, is it an honest source? Is it something you can rely on? Does it have enough information to tell you? And I'm going to show you an example about this in a second. Is this information reliable? That is, maybe it's correct once. People will run commands to tell them how close they are to time. But what happens when they're not running that command? Is there monitoring going on? Is the information logged securely? Are you keeping track of everything? And then, do you understand your timing device in your network? This is a big issue for people. A lot of people have, especially with older networks, they have a very vague idea of how everything is interconnected and where the data is moving. So I'll go through that. So the first part I want to really stress here is you got to be skeptical, right? So this is NP stat, NTP stat, which is standard. Everybody uses it. It's been the standard in the industry for many years, and there's still a large number of banks using NTP for their services. And we've gone into places and people tell us, we're getting great sync. And you go, how do you know? Well, NTP stat tells me that. Okay, so here's an NTP stat that's being pretty modest. It's saying something interesting, though. It's saying time correct to within 78 milliseconds, okay, which is pretty modest. It's actually probably most likely correct. But it could be true or false. NTP stat does not have the information to tell you that. Its phrasing there is deceptive. I'm sure not intentionally deceptive, but it's deceptive. Really, if we wanted to technically understand it, it's saying, you told me this was a good clock, and I'm believing you, because I don't have any other information. And I am adjusting the clock on my operating system to track that time that's coming to me over the network. So if it's a bad clock, I can't do anything about it. And it's telling you, I can make the clock on our operating system stay within 78 microseconds of that clock, as long as the rest of my calculations are correct. So what it's got to do is calculate how good your oscillator on your computer is, whether it's going up and down, whether it's speeding up or slowing down, which they do. The fans turn on your PC, on your server computer, and the clock goes faster. Okay, it's something, oftentimes these clocks, they're extremely cost-sensitive components, so they'll fail. I'm estimating the packet delay that's coming from your clock, and I need to know that packet delay in order to be able to see how fresh the time is. How good's my estimation? How well am I estimating the time? So it's giving you, if you qualify this thing out, it's not telling you, it's really should be telling you something much weaker than the time is correct within 78 microseconds. It's really telling you, I'm tracking, as far as I know, the time to within 78 microseconds. So, milliseconds, sorry. I got it, I'm advertising for it. So here's a conundrum that you have is, how do you check the time inside your operating system, which is the time that goes to your application programs? How do you check that against your external reference, right? Because it's inside the computer. And these computers are not designed with a bunch of high-quality A to D going out of them, right? You can't actually put a signal out that gives you precisely, what would be nice is if you had 64 bits of really high-precision clock coming out and you could just measure it as it came out. But they're not designed for that. The server computers that we use in finance are not designed for that. They're designed to maximize throughput, and they don't really care very much about I/O latency. So the question is, how do you check that? So how do you know whether the NTP stat is just making it up, or anything else? How do you know whether Timekeeper is just making it up? So the way we do it for our software is we're trying to validate our software. We've got a lot of technology that works at trying to validate how good the time that we're getting in is, how close are we synchronizing to it. But you need an external instrument to really get a grounding for that. And in this case, I'm going to show you something with the Paragon X from Calnex. Calnex is mostly involved in the telecom industry, where people actually have to measure down to nanoseconds. So they make a box, and the box is essentially a self-contained PTP server, among other things. And we're trying to measure our time inside our server computer to the time on that. And how do we do that? Well, what I'm going to show you here is sort of a diagram of how we're going to do the time. So here's our Timekeeper software that's running inside the server computer. And it's adjusting the operating system time to what it gets over the network. And it's estimating how good it is. But we're going to have it do something else, too. What we're going to do is we're going to have it reach out to a pulse per second in a peripheral device. So I've got a peripheral device with its own clock in it. And I'm going to adjust that clock over the PCIe bus and try to get that clock as accurate as possible, and then tell it to generate a pulse per second. So that pulse per second this device is generating is going to track my internal operating system clock, right? Does that make sense? It's kind of a conceptually weird idea. But I have an internal operating system's clock, and I want to I'm trying to, sort of get psychoanalyze this computer and find out what it thinks the time is, even though it's locked inside it. So what I've done is I've plugged a device with its own clock into the PCIe, the high-speed bus on this computer, and I'm having the software reach out and adjust the time on that device, and then that device is generating a pulse per second. And then I'm feeding that pulse per second back to the Paragon X. And the Paragon X is generating PTP for me. So my Timekeeper device is getting PTP from the Paragon X, and it's trying to adjust the operating system clock to that, and then it's reaching out to this peripheral device it has, and it's generating a pulse per second from that, which is going back to the Paragon device. And the Paragon's going to tell me, are you on, is it right or not? So now I have an external reference that's very closely correlated to this invisible time inside my system. And so here's an example. This is the ITU G8273 test, which really is not appropriate for enterprise timing at all, but it makes a nice little graph here. This is actually an early one. And so you can see, if we're not doing anything else to this system, we can track time within a very, very tight balance. So here's my system. It's generating a pulse per second, and the Paragon is telling me your pulse per second is right on the nose. I mean, for telecom, this would not be right on the nose. But for enterprise computing, this is right on the nose. I'm well within, what I'm like maybe 100, 200 nanoseconds here on this system. So the next thing I'm going to do is, now that I know that my basic time, that my estimates for time are reasonably accurate if I have a good time, I'm going to then take in multiple time sources and compare them to each other. And that's sort of the foundation of Timekeepers' approach to reliable time in the system. We say we want to take in multiple time sources over the network. We generate a model of each of those, and we compare them all together. And we actually do something that's kind of very primitive with this. We say the configuration has to tell us which is the best time, all right? Because we can't figure that out. We don't have the information to figure that out. You can tell us this is the best time, or you can actually tell us these guys are all very accurate. But normally what you'll have is one or two good sources, maybe three good sources, and then a couple other ones that maybe aren't that great. But here what we're showing is a couple of good sources, and the other ones are bouncing up and down in comparison to that. And it's extremely useful, even if you have bad sources that are your secondary or tertiary sources, they can, among the many differences between enterprise time synchronization and time synchronization in telecom is that we can do things like we can take 10 minutes of time that we're getting from a bad NTP source and generate a really good frequency from that, right? Which is something that we can't do otherwise. We throw out a lot, we do a lot of filtering, we generate a good frequency, and that allows us to cross-check even if it's coming over the network, the internet, and it's not that great. It gives us a cross-check, and the cross-check is absolutely key. One of the things that we've seen from our customers, sometimes our compliance tool does this thing where it will give a warning if any of the sources are starting to wander. And we've had people complain to us, so why don't you only tell us if the primary source wanders? We don't want to know if the secondary or tertiary source wanders. And what we try to explain to people is we don't know which one went wrong, or if any of them went wrong. Maybe your local oscillator has broken, right? All we can do is tell you we're trying and something funny is happening. And that's when you have to use your brains and figure it out. So you know, it's a key thing for people. People don't really appreciate how difficult it is to know anything for sure in the timing domain. So you need a lot of tools. That's the other thing. If you're maintaining a big enterprise network, you need a lot of tools to manage the data. So here's an example of what we do. This is a Timekeeper server. It's serving time out to, in this case, I think it's a couple hundred clients, and it's getting the information back from them. Each one of them is telling it what its estimate of how accurate it is. So you can kind of see that, you know, we've got some pretty good time in the core, but there's some guys who are wobbling a lot. And in this case, those are actually clients that are out in something that looks a lot like the cloud. So, okay, you can tell sort of vaguely from this that there's something wrong, and you can drill down and say, only show me this one, which one is right and which one is wrong. We have a thing called Time Map, which goes out and gives you a visual picture of what your time distribution. I showed this before in my earlier talk. It's absolutely invaluable, because otherwise you don't know where is my time coming from, where is it going to, who's using it. If I look at that other diagram, the one I just showed you before, and I go back to this one, I can sort of see maybe logically, you know, in terms of the geography of my network, who's having trouble. Maybe there's a switch somewhere in the way that's causing a problem. But if I can't, you know, do some analysis on that, I'm not going to be able to do it. So the other thing is you got to come to terms with the quality of your network. Okay, what we're showing here is this is Timekeeper. The blue is the averaged out time, the compensated for time that we generate after doing filtering and averaging and, you know, curve fitting and all the other things we do. And then those spikes that we're seeing are packets that come in unexpectedly. They're either, you know, way ahead or way behind what we think the time should be. Okay, and we're filtering those out. So we're keeping the time steady, but we're filtering it out. And this is something people in telco have looked at these graphs and they go, this is like, you can't do this. This just doesn't work, right? I'm like, yes, I can do this because I'm running on a commodity network. The commodity network, everything is statistical. Nothing is super reliable. I have to be able to filter errors because there is nothing else I can do. That's the way this network is. So you have to sort of come to terms with that. And then you have to, don't break it, right? There's a limit to what you can do. This is the same network with a little bit more stress. And you can see we're kind of holding to the thing down there, although my scale is all screwed up. But those are the outliers, right? If your network is bad enough, your outliers are going to overwhelm you. And it's pretty easy to get a network that's bad enough. So in enterprise, we often have really high quality networks, but you have to maintain that, and you have to keep track of that, and you have to make sure that nothing, you know, funny is going on in your network. And you have to be able to understand, I can filter out, I have to be able to filter out a certain number of these things, but I can't just blow it away. So I want to rush through this complex example at the end here. This is an example of misuse of Timekeeper, and how Timekeeper kind of helps you get around it. So I've got 3 sources here, and you know, it's actually also an example of very bad slide making, as you'll see in the next set. But here, this one that's labeled green in this picture is one source, and what I'm showing is that we're actually able to track this pretty close to 0. We're keeping track on it. It's Windows 10. It's not going to do great, but we're within a few microseconds here. And then I have 2 other sources, and they're offset by 1.8 milliseconds. Okay, so I look at this graph and I don't think about it, and I'm thinking, okay, I have 1 good source and 2 bad sources. Okay, but remember, my time synchronization stuff doesn't know anything about these sources except for the information it's getting, right? It's telling you that you said this is the primary source, and I'm telling you how close I can keep to it, and the other guys are off from that, right? So, you know, if we go back to this, we can see that, you know, we're nearly perfectly synchronizing to what's labeled green here, and the other 2 are off. And now I have to confess my clock sync, my slide making failure. I changed colors in the middle of this thing, but I'll explain it to you. All right, so what was used to be green is now orange up in this thing. And what I'm looking at here is not how closely we can track it, but what we're estimating is the one-way delay to it, right? And so that suddenly gives me a big warning. it says the one-way delay to that guy is way higher than the one-way delay to those guys. Now, that's not always the right warning. I might have a terrible source right next to me with a very short one-way delay, but in this case, that one-way delay is the key. It tells me what I need to know. And so I go back and I look at what those devices are, and the ones that's green and blue here, one is GPS, and the other one is a local PTP source. They're both super accurate. And that other one that I was tracking before, it was my primary source, is NTP over the internet. So I know, because that's it's an easy one, I can tell that I had them reversed in order. I should really tell Timekeeper, track your GPS source first, and then cross-check it with your PTP source, which is doing very well. And then the other one is a fallback if everything else fails. Okay? But all this sort of stresses the need for an intelligent IT team that really sort of understands what's going on, because this is, it's complicated networks here. So I'm almost done, and Pat's not paying attention, so I can take another minute or two. So then another piece of instrumentation I wanted to show you is you can track back. So this is just a picture of what the GPS, what it looks like from the GPS antenna that's sourcing us. In fact, that same GPS source that we were looking at earlier. And you can see it's a pretty good GPS source. That dark color is where we can't see the sky. And we're getting a pretty good signal. So you can archive data and make it accessible. That's another thing you need to do. And then I'm going to finish up by saying, OK, this is my plug I have to do at the end. I would say the biggest barrier, especially to New York banks, in meeting timing requirements is Google and Facebook are hiring in New York. And it's hard for them to keep really high-quality IT staff anymore. And some of them are starting to at least do a little bit more effort. But if you don't have really good IT staff who can understand complicated things like that, like maybe you reverse the order of your things, or maybe your network is not set up properly, or at least maybe there's a firewall somewhere that's doing something, it's very easy to think that you're doing well and not to be doing well at all. And that's the end. There you go.